At this point, we've talked about the pseudo-inverse as a way to solve the equation y is equal to ax, where a is not squared. And we found that the pseudo-inverse gives us the minimum norm solution and the least squared error solution, all in one. So now, as we did before, we're going to add an error term to this and see what happens. So we'll define two things here. The first is we have this case y is equal to ax plus e, and we'll say that our least squares solution is equal to a pseudo-inverse of a times y. And that then comes out to be a dagger a x plus a dagger e. So, what is the impact of the pseudo-inverse on e? We already looked at what happens when we were actually just finding a inverse times e, and we found that we could explain the maximum and the minimum error in terms of the eigenvalues of a. Well, we now have something different. We have these. We don't have eigenvalues anymore. But let's go ahead and define, for comparison, the clean situation. And we'll just say that y clean is equal to a times x. Correspondingly, x hat p inverse is just equal to a dagger y clean is a dagger a x. And just to illustrate that we're talking about the same x in both cases, I'm going to put x naught in both equations. So we have the same x, and presumably we have some clean observation also. We want to compare how does our least squares solution compare with our inverse solution. So our pseudo-inverse solution. To do this, x hat e squared minus x hat squared is equal to a dagger. Now the only difference is going to be a dagger e, because they both have the a dagger a x naught term in there. 2 squared, and so this is just going to be v sigma inverse u transpose times our error squared. Okay, so the error could be anything. Let's restrict e to be something that has unit norm. Then, what is the worst case reconstruction error? This would be our main concern. So, we can write this as a maximization problem. We want to maximize using e as our dependent variable with the constraint that it has a norm of 1, the sigma inverse u transpose e squared. Well, we know that the columns of U are orthonormal, and therefore we know this. We should pause for a second and ask what we do know. Well, if U was actually square and it had orthonormal columns, then it would span the entire space Rm in which E lives. And all we would do is we would be taking E and rotating it within this space, but without stretching it in any way. It has the same norm. And that's easy enough to see. If we have orthonormal columns, then we would get something along the lines of U transpose E, U transpose E, which would be E transpose U, U transpose E, which is going to be E transpose E, and we see that the U transpose goes away. However, I need to make a note for U in R m by m. We don't actually have that. We have a U is in m by r. So we don't actually span the whole space in which E lives. What does that mean? That means that U is going to represent some aspects of E perfectly, and other ones it will eliminate. So result is that UTE squared is going to be less than or equal to E squared, and then we can find the max beta in RR, where beta is equal to 1. Okay, so that enabled us to simplify things just a little bit. And what else do we get? Well, as before, we've got an orthonormal projection going on here. So this is going to look something like this with V beta V beta, which is just beta V transpose V. And we know what to do with the V transpose V. We've seen it lots before. That's equal to the identity matrix. So this is just equal to the norm squared of inverse sigma times beta. Okay, well, we're getting closer. When is this going to happen? Since the norm of beta is equal to 1, and since sigma is diagonal, the maximum will be achieved when beta has a 1 in the position corresponding to the largest value in sigma inverse. in other words, we can write this as beta that achieves the maximum is equal to beta r is equal to 1, and beta I is equal to 0 for I not equal to r. If that happens, we already happen to know what that value is. We have that our max is now equal to 1 over sigma r and since it's norm squared, we'll have a squared there. Okay, so that's our worst case error. So if if norm of E is not equal to 1, then we just define E hat is equal to the normalized E and find the max for E hat because it has a value of 1, and then substitute E is equal to E hat times the norm of E, and that would yield X hat least squares, so that's the one where we have noise minus the clean case is equal to V sigma inverse U transpose E and that is less than or equal to 1 over sigma r squared times the norm of E squared. So the smallest singular value causes the greatest growth in the reconstruction error. Yeah, let's just put that right here. So the smallest singular value causes the greatest reconstruction error due to observation noise. Right there. Okay, so we can actually go through the same type of analysis to bound the error from below as we just did before. We get this 1 over sigma 1 squared times the norm squared of E less than or equal to X hat LS minus X hat for our clean. Maybe I should have labeled it that way. I'm not going to go change it now, but if that helps, think of it that way. sigma r squared e squared. So this is very similar to what we had before. What we had before with square matrices was that the error was bounded by the eigenvalues, and here it's bounded by the singular values. So the same principles hold. So we can also talk about, as we did before, what happens if we just characterize that error as noise, which makes a lot of sense, fairly easy to do. So if we assume the error term E is additive Gaussian white noise, that is, each term, each entry of E, of the vector E, is normal, zero mean, and each entry in E is independent of the others, namely in this case expected value of E m E n, because it's zero mean, is just equal to 1 for m equals n and 0 for m not equal to n. No, that wouldn't be right. That would be nu squared, not 1. There we go. Then, as before, when we discussed linear inverse problems, the expected value of the norm of E squared is just going to be m times nu squared. And so the expected value of A dagger E squared is going to be nu squared times the trace of A dagger transpose times A dagger, which is just equal to nu squared times the sum of 1 over sigma r squared. Okay, very similar once again to the square case, except now we're using singular values instead of eigenvalues. And one significant difference is there are fewer potentially singular values than, even if we could have the A is square but not full rank. We could do a singular value decomposition. We could find a pseudo inverse, and we could find the error terms that show up there. But now we're summing up fewer terms, just r equals 1 to capital R, inverses of singular values, rather than all the others. And what's left off? What's left off are the ones that would have been 0. So when we try to invert something that is not invertible, it's essentially the same thing as dividing by 0. That's what makes it not invertible. So when we are doing inverses with singular values and doing the pseudo-inverse, we do the inverse of everything that we can, and then the singular values that would have been 0, we just truncate, and we only use the R non-zero values. So we'll talk about that more in the next lecture.